This is the Unit 1 or Unit 0, depending on the title, test review worksheet. I'm going to go through for this Math 2 worksheet. I'm not going to do all of them. Some of them are little answers may vary, but I'm going to give you most of them here, so hopefully it helps you out. As you do this, I would recommend you've already tried all of these problems and you go through and use this as a way to check your answers. I wouldn't also necessarily watch the entire thing from beginning to end. Skip around, find the problems that you need as I go through there. So I'm first going to start with number 2. What is the sample space for a single roll of a 6-sided number cube? If I have 6 sides, I have a sample space of 6 values. That's 1, 2, 3, 4, 5, and 6. Now, if I have a spinner that's equally divided into 4 sections, and the sections of the spinner are 1, 1, 2, 3, and I spin it 3 times and I need the sample space, this is a little bit different. So actually, it's more like the 1 takes up half of it, and I have 2, 3. So it's not really like I have 4 options. I only have 3. Now you could go in and draw a tree diagram from this, where you have 1, 2, 3, break it off into 3 branches. Then the second spin, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then you'd have 3 branches from each of those with 1, 2, 3. And then all of those could be put together to be your sample space. There's actually 27 different outcomes from that. So you could get 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, and it actually goes on 27 outcomes. And we could also see that because we had 3 options for the first spin, 3 options for the second, 3 options for the third, so 3 times 3 times 3 does give us 27. Now, 2 flips of a coin. Looking at number 4, our tree diagram, we could have heads or tails. Then this splits on the second flip, heads or tails. So I could read it as heads, 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 tails, tails, heads, tails, tails. Now if I took that and then went to 3 flips, we'll just borrow this from our first one. We can then from each of those create new branches, heads, tails, heads, tails, heads, tails, heads, tails, and this would actually give us 8 different outcomes. And those 8 outcomes are heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay, now in number 6, we have a Venn diagram. We have a baseball team with infielders and outfielders. So we have our infield and our outfield. And we're given here that 11 team members play infield positions, 8 play outfield, and 4 play both. So I'm going to start with both in the overlap because that goes right here. Now 11 play infield, so that means within the infield circle I need to have 11 total. Well, 4 of them play both, so that leaves me 7 in order to get the total of 11. Now, if I look at the outfield, I have 8 play outfield. 4 of them already play both, so that get that total, this would have to be 4. But we're not done yet because there are 22 players on the team. Now, those 22 players have to be added for and accounted for somewhere. Right now I have 15 total in my Venn diagram, so that leaves 7 that need to be on the outside. Now, the 7 that are on the outside, they could maybe be considered pitchers. They don't play infield or outfield, or they just ride the bench the whole time. But we have to make sure that everything is accounted for. In number 7, we have our 2 circles. One is the ones that have flown, and the ones that have driven. So typically with Venn diagrams like we did on number 6, I usually look for that overlap to start. So 95 total tells us what our total needs to be. 40 have flown, 60 have driven, but 25 have done both. Now that's the overlap, because now that I know the overlap, I know that 40 total have flown, so that whole circle has to add up to 40, so 15 goes in the fly only. Same idea with the driven. 60 total have to be accounted for. I already have 25, so that leaves 35 there. Now, we have to double check. Right now, this adds up to be 75 total. Well, what about those that didn't do either? That would be the 20, have neither flown nor driven. That is actually the answer we need for number 9, haven't flown or driven. And then in question 8, how many play infield? And only infield, that is 7. So we already had that information in our Venn diagram. Now, in number 10, what is the name for two events where the probability of the event happening does not affect the other? We call those independent events. Now, it asks for an example. I'm not going to give you an example here. You can look back in your notes, look back in your homework, or I also have other videos where I talk about independent events. Give you some examples. Number 12, what is the name for two events that cannot happen at the same time? We call those mutually exclusive. And again, I have other videos to that should give you some examples, so I'm not going to answer the 13. You got to find that one on your own. Okay, let's jump down to 14. Bag contains 40 marbles. That's going to be pretty important for us. 14 are red, 8 are blue, 6 are white, 12 are green. We need to write our answer in a fraction reduced. So we need probabilities. So probability of a red. Now I know it's out of 40 because that's my total. 14 of them are red, so that leaves me with 7 out of 20. Probability that they're green. I have 12 out of 40 are green, which is 6 out of 20, or it becomes 3 out of 10 once it's reduced. Now, blue or white. So I have 8 that are blue, 6 that are white, and that's going to be out of the 40. So that's 14 out of 40, which is 7 over 20. Now for 17, it's the probability it's not red. Now, not red means it's either blue, white, or green. So I could add those together and say 8 plus 6 plus 12 over the 40, and I get 26 over 40, or 13 over 20. You could also find the complement there and do 1 minus the probability it's red, which we found to be 7 over 20, which we get 20 over 20 minus 7 over 20, and that's 13 over 20. So it is the same answer, and it should be when we solve that. For number 18, a spinner divided into 12 equal sections. I'm going to write out the numbers of 1 through 12 just to give me a reference. Okay, so first the probability of a number greater than 5. I see 6, 7, 8, 9, 10, 11, 12. That is 7 out of 12 numbers. So that's my probability here. Number that is a multiple of 3. Multiples of 3, I have 3, 6, 9, 12. So there's 4 out of 12, or 1/3. Number is less than 10. That's 1 through 9. So that's going to be 9 out of 12, or 3/4. And that it's a prime number. Now your prime numbers are going to be 2, 3, 5, 7, and 11. So you actually have 5 of them are prime numbers. And if you don't remember, a prime number is when its only factors are 1 and itself. So 2, 3, 5, 7, 11 are the prime numbers. Now, 22, difference between theoretical and experimental probability. You'll have to go back, look through your notes in that. That was actually a section dedicated to it. But remember, experimental is an experiment. It's observed. They could vary in being different, but I think your notes will have a good answer to that. Now, number 23. If you roll a die 60 times and observe 12 fives, what is the observed probability of rolling a 5? Now, this would be an example of an experimental probability. So we have 12 out of 60, which is 1/5, or 0.2, or 20% of the time. Now, the expected number of 5s to be observed, that's going to be your experimental, or that's going to be your theoretical probability. And your theoretical probability is 1/6. We have a 6-sided die, and one of those is a 5. This comes out to be about 0.167, or 16.7%. So which is greater? Your experiment is greater that you observed, because that's 20%. So that will be the experimental. Now let's jump down to 27. A parts factory, you have 450 parts made in the day shift, and 28% of them are found to be defective. So the probability of having a defective part is 28 out of 450. So this tells us what our probability for the defective is. But if they ask for the probability that it's a non-defective, we want to look at the not of that. So I could do 1 minus 28 over 450, or 450 over 450 minus 28 over 450. And this gets us to 422 over 450, which if you divide that into your calculator is equal to 0.9378. So you would say your probability is approximately 93.8%. Now, with that thought, if the day shift they made 12,000 parts, how many would you expect to be defective? So what we're going to take here is that defective probability that we had in 27, so that's 28 out of 450, and we're going to multiply it by 12,000, because this is really the probability that something is defective. This is that, well, if 93.8 was the chance it would not be defective, this would be about 6.2% chance that something is defective. So we want to multiply that 6.2% across all of the 12,000 parts. Now this comes out to be about 746.6, so we're going to say 747 parts you'd expect. Now looking at number 29, we have mutually exclusive events. First off, if they're mutually exclusive, that means they cannot both occur, which we already mentioned. So this, without calculating, we know has to be 0. They cannot both occur. There is no and. This is like rolling a dice and getting a 4 and a 5. You can't get both at the same time. Now, if it's independent, that's different. We'll get to one like that in the next set. But the probability that P or Q, this is our addition rule. We're going to take the probability of P plus the probability of R, actually the probability of Q plus the probability of R, and we get 0.62 plus 0.12, or 62 hundredths and 12 hundredths. We combine those, and that gives us 0.84, 84 hundredths, or an 84% chance of occurring. Now the probability of that not happening is going to be 1 minus 0.84, because if it does happen, we have 84%. The not would be the other value, and this comes out to be 16 hundredths, or 0.16, also known as 16% chance. Now, for 32 through 34, these are independent, and these can occur at the same time because one doesn't affect the other. So in this one, an and does work. So if we look at 32 first, your rule for independent is the probability of D plus the probability of E minus the probability of D and E, because we have to subtract the overlap. And the overlap we really start to see when we look at a two-way table, which is a little bit further on in this assignment. So we fill in what we have. I got 0.85 plus 0.4 minus the and. Now, I don't know the and yet. They didn't give me that value, and that's why it's there in number 34. So we actually have to find it first. But if we stop here and look, if I combined those two right now, this is the probability of D and E, that's over 1, which also means it's over 100%. That's not going to happen. So if you get something over 1, or more than 100%, that should be a sign you didn't do it right. Your probability will never be more than that. So let's jump over here to D and E. For the probability of D and E, when they're independent, we can multiply the two. So I get 0.85, or 85 hundredths, times 0.4. This comes out to be 34 hundredths. So that's what we're going to subtract. We get 1.25 minus 34 hundredths, and that comes out to be 0.91. And then we want the not of that, 1 minus 91 hundredths, we get 0.09, or 9%. Now, for 35 through 38, we're listing independent or dependent. Independent One event has no effect on the other. Dependent, it does affect it. That second experiment is changed by the first. So if I roll a 2 on a die, then spin a 6 on a spinner, those are independent. The dice and the spinner have nothing in common. I pick an ace from a deck of cards, then pick another one without replacing. Because I've pulled that ace, I've changed the number of cards I have. I didn't put it back, so that's going to be dependent. If I flip a coin, and if I get tails, I roll a die, that is dependent, because if I flip a heads, I can't roll a die. And if it's a block day, you attend math class, that is independent, because you'll likely attend math class any day. It does not have to be block day, and in fact on some block days you may not even have math class, so that would be an independent. So now in 39 through 47 we're looking at a contingency table, also known as a two-way table. We need to find the various probabilities. So we'll start with the probability that E and S occur. So for this one we're looking at E is this row, S is this column. Now, since it says and, we want the overlap, so where they actually both occur. So this one's going to be 140 over 1,000, which is going to be 14 over 100, or 7 over 50. Now, it says it also wants it as a percent, and that is 14%, which we should have had from right here when it was 14 over 100. For our next one, we want D or T. So here we're looking at the D row and the T column. And if we look at both of these, we can see there actually is an overlap. So we have to find the probability of D plus the probability of T and subtract that overlap of D and T. The reason is otherwise we double count it, because if we added up all the values in D and added up all the values in T, the 130 shows up twice. So we're going to go 300 over 1,000 plus 350 over 1,000 minus 130 over 1,000. Now this comes out to be 520 over 1,000, which becomes 13 over 25, or 52%. Now for E or F, we have two columns. In this one, we can find the or here. They're events that don't have anything in common. They are independent. There actually is no overlap, though. So I'm going to do the probability of E is 325 over 1,000 plus probability of F is 375 over 1,000. I can combine them and get 700 over 1,000, which reduces to 7 over 10, or 70%. Now for number 42, we need to find R or S. And this is the same idea as 41. That is anything in those columns. There's nothing overlapping, so we don't have to worry about that. And so we're going to do 250 over 1,000 plus 400 over 1,000 gives us 650 over 1,000, which reduces to 13 over 20, but going back, that is 65%. Now D and F is where we get into a little bit of trouble with an AND statement, because D is here and F is here, and they don't have anything in common. They don't have an overlap. So these are what we'd call mutually exclusive events, because they cannot both occur at the same time. If we needed AND, like on the previous one, number 39, they actually had an overlap we could use, so this one is actually 0. Now, moving on, 44, we need the probability of E, and that's going to be 325 over 1,000, which is 65 over 200, or 13 over 40. And this comes out to be approximately 33%. Number 45, we need the probability of S given F. Now for this one, that given that it's F, limits us down. We're not going to use the 1,000 anymore. We actually have to just use this row F. And so what it's asking is, if F occurs, how many of those in category F are S? So I'm going to put the total for F in my denominator, so that's 375, and the number of those that are S is 180. So for S we get 180 over 375. This reduces to be 12 over 25, which is about 48%. or it is 48%. For 46, the probability, it's E given that R. So now we're going to move and look at just the R column. So of that R column, which we have 250, how many of those are E? And that is 110 out of 250. So that becomes 11 out of 25, which is 44%. And last one, we have not F given that it's not T. So for here, if it's not F, that eliminates this row. So not F, whoops, got ahead of myself. We want not T. So not T eliminates this column. And we'll cross out the total because we don't really need that. So not T has a total of 650 because that's the 250 and the 400. Now out of those, we need to figure out how many of them are not F. Now not F would be here. So what we're looking at for the probability that it's not F given that it's not T is this total, 90, 80, 110, and 140 out of the 650. Now that comes out to be 420 over 650, which is 42 out of 65, which is 65%.